Good morning, Dipyanti
Morning,
Taneja.
sir.
I hope you are doing postdoc at UT Austin.
Yes,
And
sir.
I am here in Poornima last 9 years, I suppose. And
Mhm.
25 years I served in Maharashtra.
Okay.
Uh, my background is electrical, electronics, computer, all three. Because three
Okay.
degrees I did in three different disciplines.
Mhm.
And I taught more than 45 subjects also from all the three disciplines.
Nice.
So it's good that I could work here in Purnima last 9 years in as a dean R&D, then as a principal here I'm working in Poornima College of Engineering.
Mhm.
So nice to meet you.
Nice to meet you too.
Yeah. Continue, please, Rahul.
Yeah, so Dipyanti, we are also going live on Facebook. So, hello everyone. I would like to introduce to you Dr. Dipyanti Taneja, my school friend and my childhood friend. She hails from Jaipur, and she's doing her postdoc from University of Texas. Which campus is it, Dipyanti?
Austin. Austin.
Austin
Austin.
campus. Yeah. So. So we were talking to Deepanti from a month's time, and she's been kind enough to give us time and teach our students. This is the first experience where somebody from representing a foreign university or somebody from a foreign university would be coming and teaching us. So I think now, without wasting much of the time, I would like you to start. Just a minute.
So I just want to thank Rahul first and just thank everyone for this opportunity to come live and teach. I have a PowerPoint. I have a few slides where I first talk about myself, a little bit about my background, so people know what I've done and what my background is, and then we'll start the teachings. I just want to begin with a small introduction about myself. I am a postdoc researcher working in the areas of electrical engineering, material science, and condensed matter physics at UT Austin. I've been here since July 2017, so it's been almost 3 years now. And before this, I did my PhD in semiconductor physics at the University of Cambridge. There's a picture of my graduation ceremony at Cambridge in 2018. Because it's such an old school. The ceremony takes place in Latin, and they have a very traditional way of doing things. So I'm bowing down, and the vice chancellor of the university is holding my hands and granting me the degree in Latin. It was a very special experience. And before this, I did my master's at University College London in UK, and an undergrad BSc degree in physics from Hindu College, University of Delhi. I had a short research experience at JNCSR, which is the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, in 2009, just before I moved to England. And sorry, as Rahul mentioned, I'm also from Jaipur. I've been born and brought up in Jaipur. I did my entire schooling at Indian International School with Rahul. So for my PhD, I worked in the area of semiconductor physics. So we worked on a compound semiconductor called gallium arsenide. And I was given these wafers. It's called a semiconductor wafer, which I would then take into a clean room and make a device out of it. So it goes from a semiconductor wafer like this into a small tiny device called a nanoscale device like that. And you have to dress up in what is called a clean room suit. So you see me dressed up in a bunny suit. It's called a clean room suit. And the main reason why you do that is because you don't want any dust particles or your skin particles or your hair to fall on a device and ruin the device. This image over here really shows a dust particle landing on a device, and if that happens, your device can get ruined. So you have to dress up in these bunny suits before you can go into the clean room and fabricate your devices. And then because my project was very fundamental in nature, I was trying to look at the fundamental physics of electrons and holes. I would take the fabricated devices into a cryostat laboratory and cool down the devices at very low temperatures. This image that you see is that of a cryostat, and you can obtain very low temperatures in these cryostats. I'm kind of going to come back to this this section in my lecture as well. So just keep that in mind that I did some low temperature studies. And for my postdoc, my experience has been more diverse. I worked on several different projects. Um, I worked on a class of materials called 2D materials, which are essentially atomically thin materials. And we made lots of devices on these materials, lots of transistors, and did electrical measurements. I also set up this equipment in our lab, which allows us to position two 2D materials on top of each other at nanoscale precision. So it took me a lot of time to design and develop this setup, and we finally have experiments undergoing using this equipment. And I also did a lot of outreach and mentoring and teaching activities. As a postdoc, you're really supposed to teach a lot of students, supervise a lot of PhD and master students. So I had a very interesting experience where I dealt with a lot of students, ranging from high school students to graduate students. So this was about myself. I can take career-related questions also afterwards if you have any. But let's begin with the teaching now. So Rahul asked me to teach the topics of Fermi Dirac statistics and the Hall effect. These are topics that I studied in my undergrad, and these are very useful topics. These are very useful phenomena which you should know about. They're very interesting. So Fermi Dirac statistics is a branch of quantum physics that describes how certain particles, certain specific particles, are distributed in a system over different energy states. So it's a statistics branch which only applies to certain particles which follow what is called the Pauli's exclusion principle. I'm sure you guys have heard about the Pauli's exclusion principle, which means that no two electrons in a certain energy state can have the same set of all the four quantum numbers. There are four quantum numbers called the principal quantum number, the azimuthal quantum number, magnetic quantum number, and the spin quantum number. And in each energy state, you cannot have two particles which have all the four quantum numbers as same. So it applies to those particles which obey this principle, the Pauli's exclusion principle. And these particles should have half integer spins. And these particles are called fermions. Particles which obey the Fermi Dirac statistics are called fermions. Electrons, if you look at electrons, electrons are a type of fermions with a spin of 1/2. Their spin quantum number has a value of 1.5, and they are a type of fermions. So the Fermi Dirac statistics applies to electrons because they obey the Pauli's exclusion principle and they have a spin of 1.5. This statistics is named after the two physicists who worked towards its development. The one on the left is an Italian physicist, Enrico Fermi, and the one on the right is a British physicist, Paul Dirac. So the two of them worked together and came up with the statistics. I think they probably worked independently and came up with the statistics that describes the distribution of particles over the different energy states. So this was a little bit of an introduction. I don't know about the background of a lot of students, but I think most of you would be aware that if you consider a solid crystal, then in that crystal, the electrons are not free to occupy any energy level that they want. There are certain discrete energy levels which the electrons must occupy. So this can be represented as this ladder of energy levels. You see each horizontal line represents an energy level, and the electrons occupy each energy level. If you consider a very low temperature, a temperature of close to absolute zero. So absolute zero is 0 Kelvin, and it's equals to minus 273.15 degrees Celsius. It's a temperature which is only theoretically possible, but not experimentally possible to obtain. That's why I've written T tends to 0 and not T equals 0. This is a temperature that cannot be achieved experimentally. So we always write T tends to 0, which is the absolute scale of temperature. And if you consider this temperature, there's really no heat energy in the system. You've essentially frozen the system down to 0K. And when that happens, the electrons occupy all the energy levels up to a level called the Fermi level. And above that, the energy levels are empty. So an energy level is filled with 2 electrons each. And the highest filled level is called the Fermi level, and all the levels above it are unfilled, they're empty states. Because each level holds 2 electrons, you will need n by 2 energy levels if you have n number of electrons in the system. So just some basics before we can start to understand the Fermi Dirac statistics. The other important concept is that of the KBT energy, which is also called the thermal energy. So if you look at a system and you have a physical process happening in that system, then the rate and the frequency of that physical process doesn't just depend on the energy of that process, but instead it depends on the fraction of the energy of that system and KBT. So E by KBT is a factor that is very important for determining the rate of any physical process. KB is a constant called the Boltzmann constant, and it has a constant value of this. It's a universal constant, it doesn't change value at all. So the fact that KBT is kind of a scale factor for different energy values in physics. If you want to find out the rate of a physical process, then you have to divide the energy of that process by KBT, which sort of takes into account the thermal energy in the system. So because we have the T factor, the term KBT is also called thermal energy. If we consider room temperature, which is around 25 degrees Celsius or 298 Kelvin, and you calculate the thermal energy at this temperature, then you get a value of 25.7 milli-electron volts. So it's not that big an energy, it's of the order of milli-electron volts, but for certain physical processes, this can still be quite a large energy. For example, if we revisit my PhD research where I talked about cooling down my devices to very low temperatures. So the reason why I had to do that was because I was trying to study the quantum physics of charge carriers, and the quantum energy separations are very small. They're of the order of milli-electron volts or even microelectron volts. And when you're trying to resolve such small energy separations, a small amount of heat energy can easily smear out the different energy levels, and you won't be able to measure them. So essentially, you have to cool down the devices to very low temperatures, very close to absolute zero. The lowest temperature I achieved was like 0.07 Kelvin, 70 millikelvin, which is very close to absolute zero. So when you do that, you eliminate as much heat energy as possible so that you only look at the intrinsic, the fundamental physical effects of electrons and holes in your system. So I hope this gives you a sense of why a lot of people do low temperature physics phenomena, why they're interested in low temperature stuff, because that really gives you an understanding of the fundamental physical processes happening in the system, where you completely eliminate any thermal effects that interfere with the quantum phenomena. So when you supply an energy KBT, then the electrons can kind of absorb this energy and they can jump to higher energy levels, even energy levels above the Fermi level. So this is an important thing to keep in mind. So I guess we now have an understanding of the statistics and the KBT energy, so we can look at the main part of the Fermi Dirac statistics, which is the Fermi Dirac Distribution Function. It's a very important function. This is a very important equation. It's a function which gives you the probability of a certain quantum state with energy E being filled by an electron. So Fe is a probability function. E is the energy of the state that you're looking at. EF is the Fermi level, the Fermi energy, and KBT is the thermal energy. So if you want to find out the probability of an energy level being filled or not at a certain temperature, then this is the equation that you have to use. This is the most important equation. I think you might, for your exams, you might even have to memorize this equation. It'll help you calculate the probability of whether a quantum state is occupied or not at energy E. E is the variable in this equation. You're calculating the probability at an energy of E. So we are going to go through a few slides now and calculate this probability for certain different conditions. So let's first consider the hypothetical case when t tends to 0. Again, as I mentioned, this is a purely hypothetical situation because t equals 0 is never possible to achieve experimentally. So, but it's an ideal situation. We always start with the ideal situation where t tends to 0. So if you substitute t equals 0 in this equation and you solve for fe, which is the probability function, then let's first consider the case where the energy is greater than the Fermi energy, where we're only looking at energies which are greater than the Fermi energy, and we solve for the Fermi Dirac distribution function. And the answer that we get is 0. So at the absolute limit of temperature, which is the absolute scale, with the absolute 0 Kelvin, and energy is greater than EF, you have a 0 probability of finding an electron. And if you solve this equation for energies less than the Fermi energy, then you get a probability of 1, which means that at absolute 0, all the energy levels above the Fermi level are unoccupied, and all the energy levels below the Fermi level are completely occupied. This is how you will represent it graphically. So you have energy on the x-axis, and you have the Fermi Dirac distribution function on the y-axis. All the energy states below EF are completely occupied, so you have a probability of 1. And as soon as you go above EF, you have a probability of 0. So you essentially end up having a step function like this. I want to stress that this is a purely hypothetical situation. This never really happens, right? Because you never have t equals 0. So, but this is the ideal case that we always start with. So in the ideal situation, when you have t tends to 0, the Fermi Dirac distribution function is a step function where all the states below EF are occupied and all the states above EF are completely empty. Let's now look at some more practical cases where the temperature is greater than 0, which is what we actually have in real life experiments. So when you have t greater than 0 and you consider the Fermi level and you solve the Fermi Dirac distribution function, then you get E minus EF equals 0, and then e to the power of 0 is 1, and you get a value of 1.5. So for t greater than 0 and at EF, distribution function has a value of half. You have 0.5 probability of finding an electron at the Fermi energy level for any temperature greater than 0. If you look at energies less than EF and solve this, then E minus EF would be a negative number, right? Because you're looking at energies less than EF. So this is minus. And when you solve this equation for any temperature and any E minus EF, which will be a minus number, a negative number, then you'll get a probability which is less than 1, but always greater than 0.5. And if you solve this for energies which are greater than EF, then you'll get a number which is greater than 0, but always less than 0.5. I hope this makes sense. You can at home, you can just try putting any number for X and any temperature for T. This should be in the Kelvin scale. And if you solve this, you'll always get a number which will be less than 1, but it will be greater than 0.5. And the opposite for energies greater than EF. So what happens if you represent this graphically? In the ideal situation where t equals 0, you had a step function, right? But if you look at t greater than 0, then instead of a step function, you have a function which gradually tails off to 0. At Fermi energy level, you have a probability of 0.5, as you see here. But at any energies greater than EF, you'll have the probability as greater than 0 but less than 0.5. And at energies less than EF, you'll have a probability less than 1 but greater than 0.5. So the red trace represents T greater than 0. This is an ideal situation, a very strict theoretical condition which is never possible experimentally, but in experiments, you instead of the step function, you see this this function tailing off smoothly to 0. So this is the main point that I want to stress, that the Fermi level is not this strictly defined in real life situations, in real life experiments. You have the Fermi Dirac distribution function doing this tailing off at temperatures greater than 0. So these are the main basics of the Fermi Dirac distribution function. I just want to ask a little question. I don't know if you can answer, but if you look at this graph, shows the step function, which is the ideal condition at 0K, and I have two more traces at two different temperatures. If you were to take a guess as to which temperature is higher, which one would it be? Would it be the blue one or the red one? These two traces are for the Fermi Dirac distribution function for two different temperatures. I don't know if I can see if someone is.
Yeah, so they can give your students, if you can answer the question in the chat box. Please answer the question in the chat box. All of us are listening, Dipyanti.
Okay.
Even I am revising my lessons of physics.
Okay. Maybe I can just give the answer in this case. So
let somebody guess in the chat box. Just wait for 1 or 2 minutes, and then probably after that we can move ahead.
Yeah, so we're looking at the blue and the red traces. The blue trace is closer to the step function, but the red trace is further away from it. And I want the students to guess which temperature is higher. Red one. Okay, yeah, so we got some answers, and pretty much everyone is saying that it's the red one. And that is indeed the right answer, because at a higher temperature, you have more probability of an electron occupying an energy level which is further away from the Fermi level. So yes, that is absolutely right. And I will reveal the temperatures now. So the red one is a much higher temperature, and the blue one is not that high. So when you have a higher temperature, the Fermi level is not that well defined. You cannot easily distinguish between the occupied and the unoccupied energy levels, and the Fermi level becomes sort of blurred. So this is a real experimental situation. That brings us to the end of the Fermi Dirac statistics. And there's lots more to read on this, but this is all I will talk about in this session today. Let's now talk about the Hall effect, and I'll just briefly discuss the basics of the Hall effect. So the Hall effect is a very important effect which was discovered by this scientist named Edwin Hall when he was working on his PhD thesis. And it's quite surprising because it's an effect that the electrons exhibit, but it was discovered before people even knew what an electron was. So electron was discovered by J.J. Thomson about 18 years after the discovery of the Hall effect. So it's quite surprising, and these kind of things do happen in experiments where you find out about an effect and then find out the agent causing that effect later on. So this is kind of like the excitement of research and discovery. So what exactly is the Hall effect? If you consider a current carrying conductor, you consider a conductor or a semiconductor for that matter, and it has current flowing through it, and you apply a magnetic field to the conductor, but the field has to be perpendicular to the direction of the conductor. Then the charge carriers in that conductor will start to experience a force called the Lorentz force. And the direction of this force will be perpendicular to both the direction of the current and the B field. B field is a magnetic field. It's a term we use in research quite a lot. So magnetic field is also called the B field. So essentially, if you look at my hand, I hope you're able to see my hand. If you have,
Yeah, we are able to see. Yeah.
Okay, if you have a conductor which has current flowing in this direction, and you apply a magnetic field which is perpendicular to the current like this, then the carriers will start to experience a force given by this direction, the direction of my thumb. And this is called the Fleming left-hand rule, where the current, the B field, the current, the B field, and the force experienced are all perpendicular to each other. This is a real phenomena that occurs in all semiconductors and conductors. So this diagram over here shows a block where you have the current flowing in this direction, you have a B field in this direction, and then the charge carriers start to experience a force, which leads them to get accumulated in one of the corners, in one of the edges. So you see the electrons are experiencing a force, and because of this, they start to accumulate on this edge. So when the electrons accumulate on this edge, and if you measure the potential difference between these two edges, you'll start to see a potential difference, right? Because there are more electrons on this side as compared to the other side. So this will develop a potential drop across the two edges called the Hall voltage. And this is basically what the Hall effect is. It's the development of a voltage in a conductor or a semiconductor, in a conductor or a semiconductor which has current flowing through it, and which has a B field applied to it in a perpendicular direction. So it, as I said, it happens both in a conductor as well as a semiconductor. But in a conductor, you only have electrons, whereas in a semiconductor, you have both electrons as well as holes, which are nothing but a vacancy of an electron. So wherever there isn't an electron, there will be a hole. And because you have electrons and holes both in a semiconductor, you will end up having a higher Hall voltage. Because when you have electrons piling towards one of the edges, you'll have holes piling up on the other edge. And it will give rise to a much higher Hall voltage as compared to a conductor where you only have electrons. So although both conductors and semiconductors exhibit this phenomena, for is stronger in semiconductors. So I want to talk just briefly about the usefulness of the Hall effect. If you're looking at pure semiconductors, if you're looking to study the characteristics of semiconductors, then the Hall effect helps you to extract some very useful quantities. For example, the density of the charge carriers and the mobility of the charge carriers, which are two very important quantities if you want to do anything with semiconductors. A lot of the properties of semiconductors depends on how many charge carriers are present and how quickly they're moving, which is the mobility. So once you experimentally measure the Hall voltage, you can extract the density and the mobility using these two equations. RH is called the Hall coefficient, which is defined by the Hall resistance, which is defined by the fraction of Hall resistance in the B field. So these are, I'm sure your teacher can help you with the derivation of these equations. There's a lot of mathematics behind this, which I won't go into, but just briefly that this Hall effect helps to extract two very important quantities, which are useful for characterizing a semiconductor. It also helps you to determine what kind of a semiconductor it is. So in an N-type semiconductor, you have more of electrons, whereas in a P-type semiconductor, you have more of holes. And depending on the polarity of the Hall voltage, you can find out if you have more electrons or more holes. And finally, I talked about the fundamental importance of the Hall effect, but the Hall effect is actually also used for developing and manufacturing a lot of devices. The most prominent amongst them is a Hall effect sensor. And these kind of sensors are used in your cars for wheel speed sensors. They are used as position sensors or proximity sensors. They're also used as Hall effect switches. So if you look at this image, you have a wheel is turning and you have two red magnets on this wheel. And the blue block that you see is a semiconductor, which has a current flowing through it. So as soon as a magnet comes close to the semiconductor, a Hall effect is induced in the semiconductor, and you develop a hall voltage, and the hall voltage is helping to flick on and off the light in the semiconductor, right? So this is essentially a sensor which is acting as a switch. I hope you guys can get it. So as soon as a magnet comes close to the semiconductor, it'll light up because it has a Hall effect being induced in the semiconductor. And finally, this figure demonstrates the usage of a Hall effect sensor as a wheel speed sensor. So you have a permanent magnet installed here, and you have a Hall effect sensor just placed very close to it. And this is your traditional car wheel, right? And it has these spikes. So as soon as the wheel is turning, and as soon as the Hall effect sensor comes in close proximity with a spike in the wheel, then the magnetic field through the sensor gets modulated. It'll start to experience more magnetic field. And because of that, more Hall voltage will be induced in it. So if you plot the Hall voltage as a function of time, then you'll see a curve like this, where for every spike you get an increase in the Hall voltage, and when there is no spike, then you'll see a decrease in the Hall voltage. And based on the frequency of this curve, you can find out how quickly your wheel is turning. So these are some useful applications of the Hall effect. I know it helps to have a motivation behind these kind of physical effects. Surely there are fundamental advantages towards studying them, but once you know that these are really used in your everyday life, you start to develop more interest in understanding these kind of physical phenomena. So I think that probably brings me towards the end of my presentation, yes, and I will be very happy to take any questions on any of the slides that you might have.
So, Dipyanti, there are a few questions in the Q&A section.
Okay.
One of the students has, his name is Shreyansh Patni. He asked how Fermi Dirac distribution is related in fabrication of nano devices.
Okay, so it's not related to fabrication. So fabrication and measurement are two different parts of a semiconductor process. You first manufacture a device using fabrication technologies, and then you measure it, right? So I would not say it's related to the fabrication, but it's once you have a device, then you can measure the Fermi Dirac distribution function in that device using electrical measurements. Does that make sense? I don't see the question. Where are you seeing the question?
So you can see there's a Q&A section. It would be just next to the participant button. Do you see that?
Yes, I see that. Yeah. Okay, yeah, I see the... Yeah, so fabrication, you fabricate the device, and then once you do the electrical measurements on the device, then you can have an idea of what kind of a distribution function there is in that device.
Great. Now, one of the students has, his name is Rishi Goyal. She has asked, ma'am, how Fermi Dirac stats is related to graphene devices?
Again, so in any device that has electrons, the electrons will exhibit the Fermi Dirac statistics in that device. So it doesn't matter which semiconductor you pick to make a device. Graphene is a semiconductor, it's a semi-metal. Gallium arsenide, silicon, these are all semiconductors. So you can fabricate devices on any of these, but it's not related to a specific device. It will depend on the properties of electrons in that device itself. It doesn't depend on the device. It depends on the temperature. If you remember the equation, then the distribution function only depends on the temperature. And actually, one thing I can probably say at this point, the smaller the device is, the higher the energy separations in that device will be. So it's not directly related to your question, but if you have smaller devices, if you reduce the size of a device, then the energy separations in that device increases.
Okay. Dipyanti, one student Lalit has asked that please explain the temperature is greater than zero graphical representation of Ft distribution. Why it is gradually decreasing?
Okay, so if we go back to the slides that I showed, if you look at temperature greater than zero, and because this equation holds, and this equation holds because the Fermi Dirac statistics holds, and when you will solve this is what you will get always. When temperature is greater than zero, this is something that you will get always. And that's why if you will plot this in a graphical form, you will always have this kind of a tailing of the step function. At Fermi energy level, the probability function will have a value of 0.5, but at energies greater than EF, the probability will be between 0.5 and 1. You don't know what exactly it would be because it's a probability, right? You don't have a fixed number for it, but it will be somewhere between 1 and 0.5. That means it won't be completely filled, but it'll be filled at least to half a level. And below EF, it'll have a value ranging from 1 to 0.5. So this is the main takeaway message from Fermi Dirac statistics, that for any temperature greater than zero, you always have a function which has a shape like this. Does that answer your question?
So I don't know whether you would be able to understand. I mean, I'm sure that people are listening to their queries. One of our Dipyanti, did you hear my question?
No, I couldn't hear your question.
So one of the person has asked that how Fermi Dirac statics how Fermi Dirac statics is different from Maxwell Boltzmann statistics.
Oh, okay. I don't want to say anything that I'm not sure of right now, but Fermi Dirac statistics holds for fermion. But I think Maxwell Boltzmann statistics is more, it tells you more about the transport phenomena um, for both electrons and holes, and for other particles as well. But Fermi Dirac statistics basically tells you the distribution amongst the different energy states. The Maxwell Boltzmann statistics is more about, it governs the entire transport in a semiconductor device, how the charge carriers get transported in a semiconductor device. That's determined by the Maxwell Boltzmann statistics. But the Fermi Dirac just tells you the main thing of the Fermi Dirac statistics is the probability function that I talked about. It only tells you the distribution of the charge carriers over different energy levels. But I think Maxwell Boltzmann is more kind of, it's more elaborate statistics, more elaborate theory, where you can predict the entire transport of charge carriers. It has a lot more equations than the FD statistics.
There's one quick question which is asked by Bridge Kishore, that is it possible to reduce Fermi energy between conduction band and valence band without applying any outer energy source?
No. To change the Fermi level, you have to do something externally. You have to either dope the material, like for a semiconductor, you can dope it with extra electrons or holes and change the Fermi level. You can apply an electric field, which will change the Fermi level, but the intrinsic Fermi level is always fixed. If you want to change it, then you'll have to apply some external effect, like an electric field or doping or band engineering and this kind of thing.
Okay. Dipyanti, do you want to answer more questions? If you can just quickly go through Q&A section and feel comfortable to answer questions.
Okay, sure. Latest application of Halleffect. I think that it's really used in as a position sensors in the cars and the wheel speed stuff that I explained. Those are some of the more prominent applications of Halleffect. think it's kind of repeated questions. Yeah, I think I've covered all the questions.
You good to go? Briefly tell that what was your journey of selecting, various institutions where you went on for your master's, PhD, and how would you guide our students to, study abroad, as well as, I mean, there are a lot of questions in my mind when, so for example, like many of these students who are working in various companies, they feel that if they want to work in the industry, the bachelor's is quite enough to, pursue a career. But you have been going on and on and on, and now since you would be joining Intel, uh, how would you guide our students, especially students who are studying in Jaipur, where you have been brought up? You have
Sure.
seen the culture of schools, I mean, the
Yeah.
school culture of Jaipur, particularly India.
Yeah.
So, in that context, what tips would you give to students to make a fruitful career abroad?
Sure, sure. Yeah, I think the trend is definitely from people having just a bachelor's degree to people going on further with their higher education and doing PhDs. It definitely opens up a lot of job options. The job that I have now at Intel, we only hire PhDs for that job. It's a research-based position, so we'll be working on the next generation of technology. So that because you'll be doing a lot of research, they require PhDs. And a lot of job roles are like that these days. So definitely, it would help to go on for higher studies. Um, I've been a student throughout my life so far, except the last 3 years where I've been a postdoc. So it definitely helps to have more education. For sure. You will get paid higher. You'll start off with on a higher grade. Um, and I think the education system in India and the Western countries is also very different. In India, I think there's a lot of focus on getting good grades, good marks, performing well in your exams. And for example, when people explain the concept of a Hall effect, they don't really talk about any applications, right? They just talk about, okay, this is the Fleming's left hand rule, you memorize the different fingers and you go in exams and write down the answer. But if you supplement the explanation with some applications, I think it helps to develop interest in that field. And that's why I decided to incorporate some applications. So I think that my experience has been that in US and UK, there's a lot of emphasis on practical applications of what you're studying. And if that can be developed, it definitely enhances the interest of students in that field for sure. So if you're getting an opportunity to maybe do an internship or work in a research lab where you see the practical applications of what you're doing, that would definitely be very, very helpful for your career in the future. And always try to read up more beyond your textbooks. In school, I remember like there was a lot of focus on memorizing and just like getting good grades, and that's what every one of us did. But looking back, I think there should have been more emphasis on hands-on experience with that knowledge. I did a lot of practical demonstrations with students at Cambridge and here. So they sort of tell you where is this thing going to be used, and not just give you information that you can regurgitate in an examination. So I think we need to shift from a more memorizing-based learning to a more hands-on learning. And if students can get more opportunity for that kind of things in our university or maybe even outside, that would definitely to be an advantage over other students. Yeah.
Dipyanti, there is this one technical question which somebody is asking, and that is that please let me know what is the use of antiparticle in physical world and quantum mechanics.
Wow, this is something that I would also like to ask someone, because this is more like nuclear physics and particle physics. This is not my expertise at all. It's one of the branches of physics that I never liked. So anti-particles, antimatter is something that I won't be able to help you with. I'm sorry. Yeah.
Great. So I think it was a fruitful discussion and a session. I'm very much sure that many of our students have a lot of takeaways. Uh,
Yeah, if you have any questions, you can also email me. I think I can share my email again if someone
yeah.
wants to do that. I'll be very happy to help. I actually had a seminar a couple of weeks ago at another university in Jaipur, and we did like a career discussion. We had like a 2 hour session. And a lot of students reached out to me about future prospects. So here's my email. If you want to email me and ask any questions, I will be very happy to help you out.
Sure. So, dear students, you can note down the email ID, and if you have any questions, you can write to Dipyanti ma'am. Keep a copy to your head of the department and Rekha ma'am so that we can follow up. And
You can
and
also add me on LinkedIn if you like. I think Rahul shared my LinkedIn profile, so you can also add me on LinkedIn.
great. So Dipyanti, now we are waiting for you to come to Jaipur and do a one-on-one session with our students. Now, since I mean that would be a wonderful opportunity to for all of us to meet and greet also. And I would like to again thank you for sparing time later in the evening when people tend to sleep in your country. So
It's been my pleasure and my honor to be here, Rahul. I would definitely like to visit Poornima and give an in-person talk when I'm next year.
great.
Yeah.
Great. So thank you everyone. Let's all say bye-bye to Dipyanti and thank you Dipyanti for having us, I mean having this session.
Thank you.
We are really thankful to you. Thank
Thank you,
you.
Rahul. Thanks for this.
Bye-bye.
Okay. Bye.
Thank